Okay, everybody, this pretest that we're talking about here is really a checkpoint. It's really a kind of where should I be on ideas of momentum? And since we haven't started much about collisions yet, this is as good a place to start as any. Number one asks, where is the center of mass of the three particles shown below? And I am assuming that you guys have all had a chance to do it now. So what I'm going to do is I'll bring up what I got for the answers on this long ago. The answer to number one, your center of mass that you're looking for in the X is 1.07. And then your center of mass that you got in the Y dimension ends up being 1.33. So you literally just take masses and then take their locations. That's all you have to do for the first one. Is that good? Is that what you guys came up with? Right on?
Yep, I got that.
All right, good. Cole and Wajir are shaking their head too, so they're onto it. They're happy. Okay, now the third one is the one that I asked you guys to do while I was getting this queued up. And it says that a mass of m and speed v strikes a wall perpendicular and rebounds with undiminished speed. And then it says that the time of the collision is t. Calculate the average force. Okay? This is an impulse and a momentum question. And you have to figure it out like this. Here is your ball, and then here is your ball going towards the wall. All right? So let's talk about momentum this way. It says it has a mass. We have to identify this velocity as negative because then after the ball bounces off the wall, and I'm just going to call this before, and we're going to say this is what happens afterwards. But look what's really important about this. Momentum is a vector. And because momentum is a vector, we have to understand that we can't have 2 plus v's or 2 minus v's. So then this question says, evaluate the average force numerically for something that was moving at 7.8, and then it says the duration of the collision is 3.8 milliseconds. This is what it's asking. This is for B. All right. But we've got to answer A first. Sorry, don't let me put the cart before the horse. Let's take a look at A right here. A says, if the time of collision is T, calculate the average force exerted by the ball on the wall. And then it says, B, evaluate this average force numerically for a rubber ball with a mass of 140 G moving at 7.8. Okay, the duration of the collision is 3.8. So we need to evaluate if the time of collision is T, calculate the average force. So what this is saying, for A, you don't know any mathematics for A. So A is simply saying, how would we find the average force? Well, the average force would be this. So A is simply asking to identify what equation do you think you'll use. And then in B, we're going to go ahead and use it. All right? B says now we want to calculate this. So F. So this is really asking you, do you understand that impulse equals a change in momentum? And now we're just left with the task of throwing these things in here. So we've got F times here, and then we have to have 3.8 milliseconds. That's a millisecond. don't leave it in milliseconds, 3.8 milliseconds. You got to put it in seconds so that all the units will come out right when we solve this. And then the mass, that's easy. 0.140, got to put it in kilograms. So Matthew, why do we got to put it in all these things? Don't forget, a force is a Newton, which is a kilogram times a meter per second squared. So everything we do is going to be in seconds, kilograms, and meters are coming up. So we got to do final velocity minus initial velocity. So my final velocity is going to be mv, and then, sorry. We've got the m standing outside of our change in velocity. So now we're looking for v final. My final velocity is 7.8 meters per second. Final velocity minus my initial velocity. Look how crazy that is, people. So we're going to end up doubling the number 7.8 to get our answer. So let's calculate it out and see what it comes up to. Take 0.140 times 7.8 minus 7.8. Sorry.
I got an incredibly large number that I don't think makes much sense.
7.8 minus 7.8. There. What'd you get? What'd you get for a force?
Oh, I don't think I'm right because I got 574.7 newtons, and that just...
It could be. Let's take a look. 728? 728 is what we're getting. Let's take a look at what my answer key has. Oh, it's down here. And this is 3. Who has 575?
That's what I got.
Yeah, that's the right answer.
Wow.
Well, Gio, what'd you do there? Did you do 0.0038? Okay. Calvin, nice job. You didn't screw it up. So, ladies and gentlemen, I know we don't have oodles and oodles and oodles of time left, but the real problem I wanted us to focus on today is how do we solve problems like number 2? Number 2 is similar to number 3, but they don't seem to tell you very much. It says 3 thin rods of length L are arranged in an inverted U. The 2 rods on the arms of the U each have a mass M. The third rod has 3M. Where is the center of mass of the assembly? So that wants to know center of mass for X and center of mass for Y. Well, here's what we're going to do. Let's take a look at the center of mass of this one first. Let's take a look at its MX. All right? We are going to start, I'm going to reference this whole problem with an origin right here. There's my origin. Okay, so my total mass is going to be M plus 3M plus M, 5M. My first mass is here, but it's at 0. My next mass is right here. Okay, my next mass is right here, but where is this thing? Geez, its center of mass will end up being right in the middle of that thing. So that's going to be a half. Well, its mass is 3M. And then its length will be half L. And then what about this other guy right here? Well, its center of mass as far as where that is on the grid, is going to be a full length away. So check out what I did here. I said, here, my center of mass for this bar right here, it's at 0. Because it's literally right here in this plane. Let me clean this up so that I'm not blowing you away with too much stuff. The center of mass for this object is here. The center of mass for this object is here. The center of mass for this object is here. That means as far as x is concerned, this is at 0. This is at half of an L. That's at 1 L. So since that's at 0, I do that. The 3 sits at a half. And this last third one sits at a full length L. And then I come back here, and I do the same thing for the y dimension from that origin. Okay? The first mass, which is 1m, is at a negative half of an L. Sorry, I'll be quick. The next one is at 0 because it's not above the origin anymore. And then the next one over there, that next m, is also at negative half L. And that's over 5m. So there, we just gave things in terms of m and L. That's all we had to do. Okay? I know that was confusing. We'll do another sample problem for that on Monday, but we're going to be good to go, and we'll finish our lab on Monday. You guys are wonderful. You've done a great job hanging in there. Thank you for dealing with the technology foibles. You're amazing. Have a great weekend. I appreciate you every day. Hasta la vista, babies.
Mr. Matthew?
Yes.
Is our homework just the test?